I just sent everyone an email a few minutes ago with the link to the Qualtrics survey for feedback, as well as sent the link again to where the playlist is on YouTube for all of these videos, so you will be able to access those whenever you'd like. I am going to wind up here with Lecture 4, which is a walkthrough example of what it would look like to do a model where you would need 3 levels of EMA data. So for occasions within a day, over multiple days for multiple people. Alrighty. So picking up on the previous idea here, how many levels do you need? It depends on what you're trying to predict. And if it's measured at the lowest level, then you need all of them. So most of the longitudinal examples that we have looked at so far have thought about occasions as being one dimension of time. So over days or over months, but that's it. If you have multiple layers of time, that requires multiple layers of within-person variation to reflect each distinct type of sampling. So briefly, I described the measurement burst design that the reasoning example came from in Lecture 2, where we had 6 occasions over a 2-week period. That was considered a burst, but then they repeated that burst every 6 months to look at long-term change. That would be a 3-level model for within burst variation and change, between burst variation and change, and then between person variation and change. So likewise, if you have multiple occasions from the same day, most likely there's going to be an extra correlation because they were collected on the same day relative to if they were collected on different days. Now this depends entirely on the context and what you're actually measuring, but there are ways to test whether or not you need 2 levels versus 3 levels, and I'll show you how to do that. The variance of the predictors, though, still matters. So the same rules apply, even if you're thinking of something as a day-level characteristics, for instance, how stressed you are today or how moody you are today. To the extent that people show individual differences in their average levels of that, it's also a level 3 person thing. So all the stuff about smushing holds across these models as well. Smushing/centering. So here's a 3-level model, like we just looked at, with different subscripts, because this is for a different situation. This is a model for intensive longitudinal data, in which we have multiple observations per day, over multiple days, over multiple people. So I'm calling this level 1 is time, level 2 is day, and level 3 is person. So as I promised, you can switch up your subscripts, and indeed I have. TDI, not to be confused with TMI. This is TDI for time, day, and individual. It might be TMI for me to show you this, but again, we're contractually obligated to be here, so. You're not, I am, so I'll just keep talking. So the same placeholder setup here, where I have a level 1 placeholder for what happens at level 2, and then in level 2, I have a placeholder for what happens at level 3, and I have a distinct variance component at each level, such that when you put it back together again in the composite equation, your outcome for any given time is a function of the mean of the person means, so gamma OOO as the fixed effect here, plus which person it is. If someone tends to be higher on average on this outcome, then their V would be positive. If they're lower than everyone else, their V is negative. Then within a person, once each person has their own mean via level 3, level 2 steps in, and today, are you higher or lower than your average? If you're higher, your U is positive. If you're lower, it's negative. And then within a day, I have a day level mean constructed at this point after adding in level 2. Then am I higher than lower than that day's average when I answer the question this occasion versus another occasion on the same day? So given this situation, we have sort of between persons at level 3 that's unambiguous. Level 1 and level 2 is a question. Do I really need to separate out occasions from different days and treat that separately as a level? That's an empirical question. So the way that I would go through the formation of intra-class correlations and what I would lump together and then pull apart is different given this context. So I'll show you what I think would make more sense in terms of reasonable steps of partitioning. So once upon a time there was an E. That hasn't changed. And this is variation within a day, across days, across people. First thing I'm going to do, though, is split out the people. I'm going to split out what is level 3 between person variance from what I'm calling within person variance over times and days. So this is the same idea as in the previous example in that it's how much of my variation is actually cross-sectional versus how much is longitudinal. But longitudinal in this scenario is levels 2 and 1 put together within days and between days. Then from there, I might split out what I was lumping together as within person into within day and between day and see how much of it is actually at the day level. So then I have an intraclass correlation for level 3 that I'm calling B because it's an alternative version, which is just the proportion of variance out of the total that's due to persons. And then there is relative to 1 and 2 put together, how much is 2? And that's a level 2 intraclass correlation that's different than the previous one. So the level 3 intraclass correlation, as it's defined here, as just the proportion of variance at level 3 out of the total, this is what you get out of M+ and what you get out of Stata. I don't know 3-level models well enough in R to know what they give you. Does anyone happen to know that? No? Okay, yeah, who knows? It depends on who wrote the package, right? Just yesterday, I was rerunning the same analyses with a different data set that I had built an example out of less than a year ago, and my code didn't work anymore because the function I was using was deprecated. And they told me to go find a different package and get a new function. So who knows? Who knows what they give you? It could be anything. But if you have the variance components, you can make it yourself and know for sure what you're getting. So then level 3 is just out of the total. In this version of level 2, it's out of the total that is longitudinal within persons, level 2 plus level 1, and then level 2 out of that. So to illustrate that, as well as many other layers of prediction here, so Stacy, this is closer to the steps. I'm still skipping steps, to be clear, but there's more in this case. I have a link to the full example, which I built using SAS only back when I could get away with that. And it's only 14 pages, but it's a lot. These are real data, although I selected them to give me a story that I wanted to share. So I wouldn't draw any conclusions out of this. Chris Cushing, former colleague at KU, this was one of his pilot studies that he was doing to demonstrate the effectiveness of this sort of protocol. He has an app where teenagers download it and they get buzzed several times a day to answer questions. And the app keeps buzzing until you answer them. So the parents love this app, by the way. Answer your damn phone! Because he has it programmed for maximum responsivity. Although you can also answer the questions really quickly to make it shut up, which is then, a different problem. But he was able to get almost 1,000 observations over a 20-day period from 25 different adolescents. So right off the get-go, the fact that I have almost 1,000 observations does not matter in terms of whether or not I have a small sample. I call this a small sample because I have 25 kids. So that is going to make it less appropriate and useful for me to do anything in latent variable land, single-level structural equation models, multi-level structural equation models, because all of those only have regular flavor maximum likelihood estimation, and none of them have denominator degrees of freedom, and those things matter more in terms of getting accurate answers to the variances and accurate tests of your fixed effects when you have small samples like this. So anything related to between person differences, I am underpowered for. It's basically like I have a regression model on 25 people to look at differences between people. I have much more power at the lower levels because it's not just 20 days, it's 20 days times 25 kids, and then up to 4 occasions per day. So I don't have power at this full level for the lowest level of 976 unless I have 0 intraclass correlation. So for study planning purposes, this would be great data to be able to give you a sense of intraclass correlation, to know basically what a hit to your power the fact that these are nested observations takes. So your total effective sample size will be somewhere between your real sample size and the higher level based on your interclass correlation and the number of observations within each sampling unit. That is in chapter 13 of my book, by the way. I have a whole discussion about power and effective sample size for 2-level and 3-level designs. So what I'm predicting then, I'm only using days 3 through 20 to minimize reactivity. So the first time you see the set of questions, you're likely to answer differently than the next time you see them. And so the first couple days we just sort of threw out to make sure that they knew what they were doing and we could have reasonably trustworthy data. He also went through a bunch of checks to get rid of straight lining, like people who answered 5 all day long about everything, that kind of thing. We are going to be predicting fatigue. Teenagers are tired. I know I was. I have distinct memories of being in an accounting class that was over the lunch hour where she let us do projects like at our own pace. And I would work really, really hard and use all of my study hall and everything to finish the project because once I turned it in, she let me nap. She was a lovely lady. I really needed my lunchtime naps as a teenager. When you're in sports and all the things beyond just academics and you have a part-time job and all that, I remember those naps quite fondly. So fatigue, near and dear to our hearts. Measured 4 times a day using 3 items. Each item is on a Likert scale of 1 to 5. So this is going to be a level 1 outcome. They also measured concurrently negative affect, or grumpiness as I would call it, 4 times a day using 5 items, and hours of sleep the previous night at level 2, because you can only sleep once a night, or at least the total number of hours is what we're looking at. So predictors related to time then. So this is not a study about change. This is a study about within-person dynamics, as one might market it. The idea that it doesn't matter when it is, it matters what's happening. What type of processes or mechanisms are at work, both biological, social, environmental, all that kind of stuff. But even though this isn't a study about change, I still want to make sure that I've covered my bases with respect to any time trends that are buried in these variables so that I can model that away and then focus on the mechanism process stuff. So I'm going to pay attention to time of day because I expect fatigue is going to vary systematically as a function of what time of day it is. And I'm going to use the exact time because these beeps were random. I don't have like 10 o'clock, 2 o'clock, 4 o'clock balanced time. I have unbalanced time. And at the day level, I'm going to pay attention to what is day of study and day of week as potential things that could matter in terms of predicting hours of sleep, fatigue, affect, all that kind of stuff. So first step, intraclass correlations. So here's my 3-level model. It's actually only 2 levels to start with. Note I have a 0 here to represent the idea that I have done what I described a few slides ago, collapsed level 1 and 2 into just 1 level. So between person versus within person is what's happening here. So I have fatigue at level 1 is predicted by my placeholder, beta 0. That in turn is an outcome at level 2, predicted by my placeholder, delta, which becomes the outcome at level 3, which picks up the fixed effect plus its random effect. So there's only 3 parameters in this model: the fixed intercept for the mean of the person means, the variance across people, so this is people differences in average level of fatigue. That variance component was estimated at 6.7. Skipping level 2 for now for days, such that all of what would have been level 2 is buried in level 1. And that was also close to 6. So putting these 2 together, how much of the total variation is between persons is given by using these numbers in that formula. Works out to be about half and half. So half of the reasons why some occasions are more tired than others is because some people are more tired than others all the time. At least that's what they report, right? I can't say for sure if it's real, but some people feel more tired than other people, and that's half the variability. So that tells me that in terms of my predictors, person things are going to be able to capture half the story, and things that are over time somehow, days or times, we're not sure yet, are going to be the other half of the story. So then I want to break apart this lower level 6 and ask, is there an extra correlation of occasions from the same day? If so, that will show up as a variance component at level 2. So we add that U in at level 2, and lo and behold, we do get a non-zero number there. So I've shown the calculations here because I think it helps make it a little bit more concrete as to what you would do with these numbers. So I have first computed the results of the analysis in terms of the total variance across all 3 levels. And again, I can add those 3 back together again because none of them are correlated with each other. These are 3 separate piles of variance, 1 for each level. The total is 12 something. So I can compute the proportion of variation in each level. It's 0.36 at time, 0.13 at day, and 0.51 at person. And no, it's not a coincidence that we get almost the same exact answer out of the 2-level model as the 3-level model, because we left person alone. And where the day level variance is coming from is what was level 1 before. So level 1 is splitting into 1 versus 2. 3 is left intact. And it's going to wiggle a little bit, especially because we don't have complete observations for all the people, but it will be pretty much the same conclusion. So if I do my level 3B intraclass correlation, that's the same as what I have up here. So level 3 out of the grand total is 0.51. Then I do level 2B for how much of what I'm calling within persons is actually between days versus within days. And it's day level variance, so the new level 2 variance term that I hear, right here, 1.6, divided by that plus what is now level 1. So you'll see that level 1 was 6.1. That has split into 4.5 and 1.6. So they don't add up exactly, but conceptually that's what has happened. Yes, sir?
So is the number ICC-L3 in between, is that like smushed technically? Because you haven't put it in.
This one isn't smushed. The level 1 is smushed.
Oh, okay.
Level 1 and level 2 in this model are smushed together.
Okay.
So it's answering the question, do I need a 3-level model versus a 2-level model?
I see. Okay.
But from a different perspective than the question was asked before. The question before was time, person, group. Do I need a 3-level model? Are there group differences among the people? Here, I'm assuming people differences are going to be there. They're just going to. So the question I'm asking is, do I need to split out time into kinds, within day and between day? And I do. So it works out that what I was smushing together as just within persons is 27% between day and 63% within day. Does that work? I think that's, again, my son is better at math than me at this point, but I think that sums to 1. Question, the total variance for the 2 models are different due to estimation error. Yeah, it's, when you're, basically yes, it's not an error, it's a consequence of having an unbalanced design. You would expect the totals to be recomputed more exactly if everyone had the exact same number of days and the exact same times per day. There's also a difference in terms of the estimation whether you have profiled the residual out of the likelihood or not. And in REML you cannot do that, but in EML you can. So you would get a closer sum back together if you've profiled the residual variance out of the likelihood, which I did not do. But conceptually, that's what I'm going for. The numbers are not going to be exact, but the idea holds, regardless of whether they sum exactly. So this ICC being 0.27, I can do a likelihood ratio test to compare the fit between these 2 models. So each of these models, when all is said and done, is going to give me one number, log likelihood, that summarizes the total height of each person's data summed across people in log units. That's our index of model goodness. More log likelihood is better, taller is better. But because to compare log likelihoods between models, we have to take their difference and multiply it by -2, what you commonly get on your output is the version of it that is -2 times the log likelihood directly. And that means smaller is better because of the minus. So I can take the -2 log likelihood of one model, subtract the -2 log likelihood of the model that has more parameters, and their difference follows a chi-square distribution. So if I add one new parameter, such as the variance of these U's across people in days, or just days here, then that minus 2 log likelihood should be at least 3.84, which is the critical value at alpha of 0.05 for a chi-square. So yeah, I don't remember the exact number, but it was greater than that. So that's saying that this 0.27 is not nothing. We do need it there. So we're going to keep fatigue unsmushed. So looking at these proportions then, of all the variability in fatigue, 51% is because some people are more tired than others. 13% is because some days are more tired than others. And 36% is because within a day, some occasions are more tired than others. Okay, how are we doing? Good. All right. What about negative affect? Do you think some people are grumpier than others? Odds are good. Affect is one of those words I try really hard not to use in a stats example, because then you get into things like the effect of affect. And no. So it's grumpiness. That's what we're going to call this. Same question, though, because negative affect was also measured at each of these same occasions as fatigue. So we start with the 2-level model. And here, yes, indeed, 77% of the variance is because some people are grumpier than other people. If I add in the middle variance component for differences across days, trying to partition the within person into between day and within day, only 3% is at the day level. It's still significantly greater than 0. It results in a level 2 intraclass correlation of 0.12. So of all the longitudinal variance, only 12% of it is because of which day is which. So it's a smaller effect than what we had for fatigue, but it's there nonetheless. So negative affect is going to be a predictor of fatigue eventually. And looking at these proportions relative to each other, there's going to be very little for negative affect to do at level 2. There's not a lot of information in it relative to the other levels. Negative affect doesn't really vary across the days. It varies within days and it varies between people. Doesn't mean I can't try. Just these things are useful to keep in mind as the get-go. Can't have covariance if you don't have variance. How about previous night's sleep? So this is a level 2 variable. I want to know how much of it is at level 3 versus level 2. So a 2-level model ignoring level 1 in this case, so keeping level 1 at 0 here. In this case, we have an intraclass correlation of 0.27. So of all the reasons why sleep might differ across days, 27% of it is because some people sleep more than others, on average. Time of day, so you're like, what? Time of day is an outcome? What? I'm controlling for any non-randomness in when people answered their phones, basically. And as one might expect, there was very little between-person variance. I think these numbers are labeled wrong. I'm looking at this and going, no, that's not right. Level 1 and level 3 are backwards on this. I'll fix it. Any typos that I see on the handouts, by the way, I'm going to fix later today and repost, because that way you'll have the right versions. But very little between-person variance in this case, as one might imagine. So we can think of time of day as mostly level 1, a tiny, tiny bit between person, and no differences across days. So in terms of controlling for time of day, we'll do that at level 1 for sure. Need to do that at level 3 just in case, and it's not going to go into level 2. Okay, questions so far? We have anything in the Zoom? Nope. Zoomers, you still there? Reaction time. Oh, there we go. Hello. I'm still watching you, just in case.
I'm wondering if it would have made sense to also model like day of the week, especially for teenagers.
Yep.
And if like that's where a lot of the day variance is coming from in terms of fatigue. Like I imagine that people would feel less tired on the weekends as opposed to the weekdays, maybe.
Thank you for that segue. Change over time. Oh, I have red lines. Look, these are foreshadowing things. We call that an animation fail, by the way, when things are showing up before you want them to. which, by the way, whenever I'm doing presentations and I'm going to have to use someone else's computer, rather than do animations, I will layer slides. That's a lot safer to hit the next slide and have the animation, like whatever wasn't there, pop in. So then you don't have something like this, but oh well. So I have a plot here in which I rounded time of day into the nearest half hour, and I generated separate means for each of those rounded intervals out of a saturated means model. So I note that terminology specifically because what I did not do is just calculate means in the data set. The saturated means model that you get when you actually ask it to estimate the mean is a mean that reflects missing at random as opposed to missing completely at random. If I just calculated the means from the data set, I'm assuming that anything that's not there for a particular occasion is missing completely at random, whereas letting the model do it is trying to recapture what the pattern would have looked like had the data been perfectly balanced and complete. So they don't always match, especially if you have a lot of missing data. So this is the picture that I got out of, this is Glimix and SAS that made this for me. And so then I threw the numbers into Excel and made a plot, and it looks quadratic-y to me. So it looks like people are tired when they wake up around 6, 7 in the morning. They're tired at 23 o'clock, as I'm going to have to learn how to do in European time. 23 o'clock is very late, I think. And they're least tired during the middle of the day in the afternoon. So I'm going to model this with quadratic here. Then we have a cross-day change in fatigue as a function of day of study. And I drew the line here because it looks like there's not really any trend, and there's certainly a lot of variability around these points, so it doesn't look like there's anything there. Day of the week, however, we got an outlier on day 2, which is Monday. So yeah, people are more tired on Mondays. And I have a link to the YouTube in case anyone wants to see that clip out of Office Space. So yeah, so then my unconditional model for fatigue over time is going to look like this thing. So at level 1, I am predicting fatigue by intercept placeholder and 2 slope placeholders for hour of day minus 15. So I'm centering this at 3 o'clock, basically. And hour squared is because of the previous slide showing that it looked like a quadratic trend to me, so that's what I was going to stick in there. Because I have 3 placeholders at level 1, I have 3 level 2 equations. Beta ODI is my intercept placeholder at level 2. That's going to have a level 3 placeholder for the level 3 intercept plus the level 3 effect of it being Monday and a random intercept. So Monday DI, meaning that it varies across days. So this is a dummy code. It's 1 if it's Monday and 0 if it's not. Then I have placeholders for my effects of linear and quadratic hour of the day. And I also ended up with random effects on those. So I added those in sequential steps, and they both contributed to the model, so I kept them. So this part here is allowing differences across days in that quadratic trajectory, basically the extent of the dip as well as your level of fatigue. So not all days are created equal, especially if it's Monday. Yes?
Why did you only create a dummy code for Monday? Because it looks like other days too, like Sunday looks like they're doing pretty good, and Friday.
The realistic reason is because this model is ugly enough. But, but yes, whether you need to account for differences across all the days or like weekends versus weekdays or whatever you have, those are all empirical questions to be settled with steps in many analyses. Yep. But just looking at that was the one that visually to me sort of stuck out. So. A lot of my examples, the answer is, why did you do it this way, is because I thought, this is enough. It's a practical consideration. Okay, so we have fatigue is changing throughout the day in this quadratic fashion. We are controlling the intercept for whether or not it's Monday across days, and we're allowing then at level 3 Each of these delta thingies is a placeholder that then gets defined at level 3. And so the first one is the intercept. That is your fatigue at 15 o'clock. And I am also adding in an effect of when people tended to be measured. So average differences across persons in time, that's because of the 2% of the variance that was at that level. So I'm thinking of this as a control, but I want to have it in there so that these effects aren't smushed. So it's within persons purely then at level 1 and between persons at level 2. I have random effects on the intercept, linear time, and quadratic time. That's allowing between person differences and that average fatigue trajectory across all of the days. So some people might have a bigger dip than other people at level 3. Some days may have a bigger dip than other days at level 2. Each of those is going to be predicted by average time of day as a control. And then the last but not least is Monday, where I started with a fixed effect. And I want to say that I tested a random effect and didn't need it. So then in terms of all of these different piles of variance, I've got 1, 2, 3, 4, 5, 6, 7. So at level 3, there are 3 differences between people that are in the model right now. Why do some kids report more fatigue at 3 p.m.? That's the intercept. Why do some kids change more both linearly and quadratically in fatigue throughout the day? I have in parentheses here, because I did test the Monday slope, why is there a bigger difference between Mondays and the other days for some kids than others? Looks like that wasn't significant. That could also be because not everybody answered questions on Mondays. It depends on your power, right? How many Mondays are in the sample. What I don't have here that I could have is what's known as a scale model random intercept. So this is back to the terminology of location, scale, mixed effects models. Everything that we've talked about this week has been part of what's known as the location model, which is your standard multi-level model. Scale model, the extra part, is a way that you can allow differences in the amounts of your variances as a function of person characteristics and time characteristics. So by default, this E right here gets a variance that is assumed to be constant across times, days, and people. That's probably not realistic. There's probably some kids that are more variable in their fatigue within a day than other kids. So you can also estimate what is known as a scale model random intercept, where I have to do this with the gesture. There's no other way. Some kids are like this with their variance, and some kids are like this. It's an intercept that keeps track of differences in the amount of within-person variance. So this would be the idea of inconsistency or fluctuation or unreliability, any of those words you could think of as applying to this concept. And I could have put that in here too, but again, this was enough. At level 2, there are 3 sources of variance to be predicted. Why are some days worse at 3 p.m. than other days? And why are some days different in terms of the fatigue trajectory than other days? And those would have to be predicted by day level characteristics. And then last but not least, the residual. Why is fatigue higher than predicted by the trajectory at any given occasion? What's happening at that occasion has to be predicted by time things. And so at this point, there is no way I can add these variances back together again. Because anything at the same level has a covariance to it. So what's not shown in the model, because of the way that I wrote it without matrices, is the covariances among these 3 V's. Because any V that comes from the same individual is probably going to be related because of that. The covariance among the 3 U's as well, so there's 3 of those. And then E. So this is a situation in which pseudo R-square as an effect size is going to be very tricky to keep track of, because I literally have 7 variance components here, and each of them is going to go down for a different reason. So this might be a situation in which total R-square would be more useful, or taking each of the slopes in the model and converting their t-test statistics to effect sizes of D's or R's, something like that. Okay. Now let's add in negative affect and some numbers for us to play with. This is SAS output. So negative affect is also a 3-level variable. As we discovered, 77% of its variance is because some kids are grumpier than others. There was very little variance across days, but still enough to have it in the model, and the rest is within day. If I just put in negative affect at level 1, maybe I subtract 6 or whatever, and I leave it there, what have I done? Smushed. So I can't just put in negative affect all by itself. And because I only got 25 kids, I can't make it latent without probably blowing everything up. So I'm going to do a brute force decomposition of its variance through centering. So this is where subscripts really matter. NaTDI is what this is, negative affect per time day individual, minus the mean of negative affect for that day and that person. So this is day mean centering, I guess you might call it that. Variable centering, the whole thing. But what the mean is, it's the mean at the next level is what you get centered on. So this is going to keep track of differences in negative affect relative to the mean for the day. Then at level 2, I pick up a placeholder for the effect at level 3, and the variable it multiplies is the mean for the day minus the mean for the person. So this is going to be differences within persons across days on average. Why are some days grumpier than other days? Are you more grumpy today than you usually are? That's this one right here. I also added a random slope for it. For the within day negative affect one. So I'm allowing day level differences in the effect of grumpiness on fatigue. And then at level 3, I pick up negative affect mean for the person minus some constant so that 0 means something. So I've got the 3 pieces of negative affect as main effects in the model. And so the variability at each piece has the potential to show a distinct effect at each level. And then I only have fixed effects for within day negative affect and between day negative affect. And then here are the values that I got back. So I've separated the effects into what they represent. The first 4 effects, these are fixed effects, are related to just time. So the intercept is the reference point for when everything is 0 in this model. Then if it's Monday, fatigue is higher by 0.46 on average. And then we have linear and quadratic effects of time of day. So this linear effect is specific to 3 p.m. It looks like the effect of fatigue is more greater over time. So this is an up that's going more upper, so acceleration. A happy face U, as it were, the parabola. Then we get the contextual effects of person and whether or not some people were measured later in the day on average. None of those are significant, so we don't need to worry about those. And then we get the layers of negative affect. So these are 3 different coefficients. I'm not even going to worry about contextual effects testing whether they're different from each other. I'm just going to let them be. They all represent different things. They're all positive and they're all significant, though. So at level, let's start with 3. For every unit more grumpy you are on average than other people, your average level of fatigue goes up by 0.62. So being grumpy is bad for you. Level 2 then, okay, I controlled for which person is which. Now let's go within persons. On days where I am more grumpy than I usually am, for every unit more grumpier I am, fatigue goes up for that whole day by 0.42. And then level 1, for every unit grumpier I am right now than the rest of my day, fatigue right now, the same time, is higher by 0.23. Question from the chat, why is time at level 1 not person day mean centered? I chose to do it as grand mean centering for time at level 1 with a contextual effect because most of the information is level 1. And I thought that keeping it in the metric of like hour of the day would be more interpretable than a relative hour of the day. But this would be a different choice if I were doing something like cortisol. So in cortisol, the change that occurs across the day is relative to how long you've been awake. So centering this at like 3 o'clock or something would not do you any good. In that type of situation, I would probably have within person, like relative to when you woke up as the time metric. So how long have you been awake that day, not how long has it been since midnight. And that would be the analog of person mean centering. And then when you woke up that day would go in at level 3, or level 2, when you tend to usually wake up, goes in at level 3. Okay, does that help? Okay, yes. It's a choice. So because hour is not person mean centered, it's constant centered, effect of hours up here are contextual effects. Whereas the fact that we've done this variable centering at each level for negative affect means these are all level specific effects and not contextual effects. So at this point, reviewer 3 might look at your table of results and be like, you can't have negative affect 3 times because collinearity or something. Bad. Paraphrasing. I used to do reviewer 3 as a valley girl or a truck driver, but since then it's turned into a kindergartner. But I can do my valley girl, like, you totally can't have negative affect 3 times in one model, because that's like bad and stuff, with a little bit of Kardashian vocal fry. But how do I answer? Either the valley girl reviewer 3 or the kindergartner. Why is this okay? And dare I say, necessary, not just okay. Why am I doing this to myself? Why do I need all 3? What happens if I don't have 3? What happens if I just said negative affect centered at 10 in level 1, the end? It's a smushed effect.
You're smushing, and you can't tell what's what.
Exactly. Is the effect there because some people are grumpier, some days are worse, or sometimes are harder? Those are 3 different things. And I've literally carved the variable up into those 3 different things and put them all in the model. And with respect to collinearity, do I need to worry about that? Nope. If I did the programming right, these are all orthogonal variables. I set them up that way. If I did constant base centering, if I did negative affect at level 1 minus 10, and then I threw in the day mean and the person mean, those would be correlated. But I'm relying on that correlation then to create the correct version of the effects through statistical partialing. So it's actually advantageous. So yeah, you have to be in describing models of this level of complexity. Like if you look at this, this is huge, right? Like I'm at like 12-point font or something to get this equation on here. But conceptually, I have 3 variables in this model. Time, Monday, grumpiness. So in describing what has happened, trying to orient your reader not just to this is the level 1 effect and this is the level 2 effect, but like this is some days are worse, some people are grumpier, some times are harder, like anything you can do to convey what 1 unit more than means in that context will make those effects different and necessary. Now, based on the standard errors here, I'm just eyeballing these. It looks like all 3 of these numbers are significantly different to me. It looks like I wouldn't want to smush them together. And I don't want to smush them together because conceptually these represent different things, but they're doing so on different scales. These are unstandardized coefficients. Okay, how are we doing? Hanging in there? We're almost done, as a matter of fact. But not quite. We got one more layer, or two more? Two more, okay. Two more layers. Because I still haven't answered my question about sleep. So I'm adding to the previous model to see if hours of sleep the last night predicts fatigue, one would think. So I have sleep the night before is the variable here, and it does not go into the level 1 model because sleep only happens once a day. So this is a level 2 predictor, but because it's at level 2, it's also at level 3. And I think several slides ago, the interclass correlation for level 3 was something like 0.30-ish. 30% of the variance was because some people sleep more than others, something like that. I can go back and look. We did that. It was one of the first things we did. Yep, 27%. So 27% of the variance in sleep is because some people sleep more. The rest is because some days are different than other days. So both of those go in the model. There we go. So variable centering, same idea. Today's, I don't need a mean over the sleep here. That's a copy-paste error. Today's sleep for this day minus the person mean minus 7, which was near the average for the sample. No wonder they're tired. 7 hours of sleep is not good for teenagers. So this, get rid of that bar right there. That bar doesn't need to be there. I'll fix that later too. So I just put in fixed effects of these two. I tried a random effect, but it didn't converge, probably because I've already got too many random effects in the model. So then the interpretation of these is some people sleep more than others at level 3, and then relative to yourself, how much more did you sleep last night than your usual level? And less sleep is related to more fatigue, as one might imagine, but only at level 2. So I'm looking at the p-values in here. Level 2's p-value I'm going to call approaching significance. Can I do that? 0.07. Like a cake. Like you just check on it later and it'll be there. It's approaching. It's just not done yet. 0.46 though, unequivocally non-significant. Maybe because it doesn't matter, or maybe because I got 25 kids. Don't know. This is where the world of effect sizes are going to be useful to you, to try and disentangle if it's a power issue versus a small effect, because you can't look at these numbers and have any idea as to how strong the effect actually is. All of these are on completely different scales. But it looks like sleeping less than usual results in more fatigue the next day, but kids who sleep less than other kids don't report less fatigue than other kids. So it's all about what you're used to. Last model then, adding interactions. Just like you can't smush main effects, you can't smush interactions either. So I'm answering the question, does the link between grumpiness and fatigue depend on sleep? That's a moderation question. To answer that question, I had to add in 6 interaction terms. Yes, Zoomers, we're seeing all the eyebrows go up in the room simultaneously. What? Yeah, I did. Because I have sleep and negative affect at level 2, I have sleep and negative affect at level 3, and then level 2 negative affect with level 3 sleep, and level 3 negative affect with level 2 sleep. Did I say that one? The cross level ones. And then we have level 1 negative affect times each of them. So that's where I get 6. And at this point I was like, yeah, no, I'm not showing all the numbers, but I'd be happy to get the handout out if you want to look at the giant list of coefficients. But the story was the kids who sleep more than others have weaker within day and between day effects of negative affect. So you can think of sleep as a protective mechanism, perhaps. The kids who sleep more than others had a greater between-person effect of negative affect. So the tendency for grumpy kids to be tired kids is stronger in kids who sleep more. That's my conclusion for the between person. So there were different effects across levels in the relationship of the moderation. Sleep made it weaker effect within persons. It made it a stronger effect between persons. And that would be the story, because that's enough. So the rest of this is just about centering and what happens. Basically, if you do variable centering, you're good to go. If you carve up the variables into the pieces at each level, then when it's in the model, you're only talking about what happens at that level. When you leave it out, you're assuming it's 0. If you do constant centering, then you have to worry about smushing about what's been left out. So anything that you leave out, you're assuming then is equal to the level below it, which is always a testable assumption and sometimes a problem. And I think that's it. Yeah, summary. Pseudo R-square, summary, that's a lot too, and the end. So happy to answer questions about any of that stuff, but I think that's probably overkill for where we are today. Okay. So yeah, this is where we are, intensive repeated measures data, the grand finale. There's a lot going on in intensive longitudinal data, and I don't even have all the things that could have been going on. There's nothing autoregressive in here. There's no scale model in here. I could have used latent variables because all of these, like negative affect is a sum across items, and fatigue is a sum across items, and to do that more properly should have been latent variables, which would have made this a lot worse. So it does get very complicated, but cool at the same time. So those of you who have intensive longitudinal data, does anyone want to talk about what you now plan to do that you maybe didn't know before? Or are there questions about what one could or should do? So I know a couple of you have data that you mentioned to me at one point. No one wants to share? Or share more, I should say.
I guess my plan is to work with a methodologist.
Your plan is to work with a methodologist. Fair. Fair. Yes, and keep in mind, folks, that this is my job. Like this is my content area. Like this is the thing that I read the most often, I'm most known for, I spend thinking about, and it's still really freaking hard. So if you are a psychologist, an educator of any other kinds, and you have a content area, don't beat yourself up for not having this be your content area too. It does take a lot of focus, and yes, that's why methodologists are here, is in part to work on the development of to be able to do these sorts of models and estimate them and trust them, but also then to collaborate with other people and make sure that these developments get out into the literature where they belong. Different parts. I had a department chair once who said that faculty are not like checkers, they're like chess. We all have different roles to play on purpose, and you don't want to treat people as if they're interchangeable because then that's not helpful. So we all do different things. Question from Yan Chen?
Hi, Dr. Hoffman. First, it's really relieving to and because I was about to pull my hairs off, but a couple of questions. One is in the field of, well, I know in most field, we want to control for theoretical plausible covariates.
Mm-hmm.
When we control, for example, in this model, I do not see any like gender or any demographics. So when we control for covariates across different levels, can we live with smushing them together, or do we still need to, okay, I need to partition them into level 2, level 3?
You still need to unsmush them, is the short answer. Because if you fit a smushed effect of a covariate, and that covariate's effect is not fully in the model in the way that it's supposed to be, then you haven't really controlled for it.
I see, but most of the time the covariates we want to control is categorical. For example, like race, gender, or family, education level.
Yes. So in this example, any person-level characteristics that I want to put in as controls would go in at level 3, which means I don't have to worry about smushing at all. because if it's measured at the highest level, that's all you can do. It doesn't go down. They can only go up.
Gotcha. If we have, like, for example, day nested in, present nested in class,
Then anything that's a person thing is also potentially a class thing. And you can check. I would do this as a policy always, regardless of whether you're thinking about a particular variable as a control, a predictor, an outcome, or whatever. If it's measured at a lower level, check its ICCs. See where it has variance, because where it has variance, it has the potential to show an effect.
I see. Yeah. And actually, that leads to my follow-up question is, could you please elaborate a little bit on, like, I know most of in this class we've been talking about is like deep into the details and all the predictor, variance, decomposition. Take a step back, think about model. So model fit and how we determine if our model holistically is a good one, or we should proceed to make it more complicated. So do we follow the old rule, like regression, check the pseudo R square, or like likelihood ratio, or?
So those, I think you're hitting at different ideas of what makes a model good. There's what makes a model good in the sense of prediction. So R square, for instance, and effect sizes of your individual variables, like how effectively have I predicted fatigue, is one way of answering that question. What makes a model good in terms of fit, like in an SEM context, that means has my model adequately recreated the variances, covariances, and means of my original data? And I can't answer that question with this data set because it's completely unbalanced. There is no single covariance matrix I can come back to that holds the right answer, against which I can compare my model and see how much worse it fits. Because everybody has all these different time occasions. If I pretended like everything was exchangeable, then potentially I could wander into the world of multi-level SEM and I could have fit at each level with my boxes, but I've got 25 people, and it's not going to go well. I think that, you can, to the extent that you can phrase alternative possibilities as testable hypotheses. Like, do I need a random slope for this? Well, I don't know, do you? Put it in the model and see if it helps. And keep in mind that your power to detect random slopes depends on your sample size. So I have a lot less power to detect random slopes across people because I have 25 people, relative to random slopes across days because I've got 20 days times 25 people. And significance tests for fixed effects have the same limitations in terms of power versus effect size. So there's not an easy answer as to whether you can be sure that your model is good enough or that you'd come to the same conclusion if you started the process in a different order. I think all you can do is defend what you've tried to do in the light of what other people have done and what seems reasonable. I know that's like hand-wavy, but it's true. There's not a right answer in this case.
So is it possible if we, for example, because all the models we build is actually nested within each other, so is it, from what I hear you say, it seems like we just need to run the -2 LL to see how much meaningful reduction.
So it depends on your estimator. So one of the details that I skipped is what is allowable for model comparisons when you're estimating it using maximum likelihood versus residual maximum likelihood. If you're in straight up maximum likelihood, you can do a likelihood ratio test anything. You can compare models that differ in fixed effects, random effects, both kind, whatever. In REML, likelihood ratio tests are only valid for variance component differences. The fixed effects have to be the same, otherwise they're on different scales. So in this situation, I can't do a likelihood ratio test to answer, do I need these 6 interactions, for instance, because this is REML. But what I can do is a multivariate walled test, basically lump all those slopes together and ask for a custom F test as to whether they improve the model. That is the same thing as what people do in stepwise regression. So the test of the R-square change that you get in stepwise regression, that F test, you can build that F test yourself out of a single model rather than doing it in layers, always.
I see, yeah. And thank you so much. And one last question, then I will shut up. So do you have any procedure to decide when we want to add the higher order term of time? For example, like quadratic, cubic. I see you look at curve and is there like some cheat sheet, or for example, if it curves that way, we add quadratic.
My process is make a picture and think about what the picture says versus like theoretically what I know about the variable and try to decide on a family of models. So I picked the polynomial family because this looked like a continuous function, and I thought it was reasonable that fatigue would dip during the day and then come back up as people got closer to bedtime. At least that's what happens to me. And it's an empirical question from that point, what order of polynomial is sufficient, because you can add in higher order terms and see if they help. But making the picture, I think, is important as a first pass, because you can get a sense of, like, is this going to be a piecewise model? Like, do the slopes look discontinuous, or is this more continuous? Is it straight? Is it bendy? Is it bendy where it levels off, or bendy where it comes back down? Because those are different things. Exponential would be better for bendy that levels off versus quadratic for comes back down. It's a combination of art and science, I would say. But making a picture of the means across time as estimated from your model is the first step. I would always do that.
Thank you. Yes.
Okay, sure. What else? I have a couple comments, by the way. People are feeling better, that they don't have to be methodological experts, as well as their own scientists in their own area. And I keep referring to, like, when I used to be a cognitive aging person, because yeah, at one point in time I tried to keep up in multiple disciplines, and I had to let it go because I didn't, there's only so many hours in the day, and I wasn't teaching those classes. I was teaching these classes. So plus this stuff is way cooler. There's that inherent bias as to what wakes you up in the morning, and for me it's this, for better or worse. All right, what else? Anyone else want to ask questions? Make comments?
Can we walk through the variable centering for the 3-level models again at each level?
Yes. Like negative affect to start with?
Yeah.
Back a couple models? Or this starting here?
We can
Start here?
Yeah.
Okay. So this time of day thing is because I had an interclass correlation, and again, these are backwards, because I changed it halfway through whether I was 3, 2, or 1 in the right order, so I know this is wrong. Most of the variation in, this is wrong because it doesn't sum to 1 also, so this is a copy-paste problem I got to fix. But what I remember happening is that time of day, most of the variation was at level 1, which is what you would expect. But I wanted to see if there were systematic differences in when people were responding. Because if someone tended to respond later than someone else on average, that's a between-person difference, even though it's time of day. And I want to make sure that that's a separate effect in the model. So I was thinking of this in the cortisol context of, like, if you wake up later in the morning, does everything look different from you after that than somebody who wakes up earlier? And I think people could indicate when they wanted to be beeped as their range, and because they could indicate that, that's a potential between-person difference. So I fed time of day into my intraclass correlation machine to figure out what the variance is at each level. There was a tiny bit at the top, none at day level, and most of it was at the bottom. And so to deal with that then in the model, I have hour minus 15 and hour minus 15 squared at level 1. And then I also have mean hours minus 15 at level 3. These are contextual effects. So these are there purely to make sure that what I'm talking about as within day is actually within day and not a little bit contaminated by between-person differences and when they got buzzed. So that's the reason I set it up that way. Monday, I would have had to have checked if people had different numbers of Mondays, and I don't think that happened, and so I just treated this as pure level 2. Then when we get into negative affect, so I have the negative affect at that time for that day for that person, so this is not a mean of any kind, minus the mean for the day. So this is, am I grumpier now than I am the rest of the day? That's level 1. And then the mean for the day, so this same variable that's being subtracted is what starts the next one, minus the mean for the person. So then this captures, am I grumpier than I usually am today than my usual mean? And then, again, the part that's being subtracted in level 2 comes out front to lead the level 3 term. And here, I just subtracted a constant so that this has a meaningful 0 point. So then the level 3 term is person differences in grumpiness. The level 2 term is differences across days from the same person in average grumpiness. And level 1 is differences within the same day in grumpiness at one occasion versus the next.
And so in most cases, at level 3, it would make sense to subtract the grand mean from the individual's mean.
Something so that that 0 is a meaningful value. So 10 was what the data said, and so I stuck that in there, but which constant you pick does not matter. It really doesn't. For constant centering, the constant is irrelevant because constant centering does not split variance. It's all still in there. And then sleep, and this one was the typo, so this should not have a line over it because this is not a mean. This is just the sleep for that day for that person minus the person mean. So this is like what we did yesterday, just the 2-level demarcation, except it's levels 2 and 3 in this story and not 1 and 2. And then, then interaction palooza, and that's where we left off with that.
Thank you.
Sure. Interaction palooza. Kind of like Lollapalooza, but way less fun. Unless you're me, in which case it's more fun. All right, anything else? Then are we okay with calling it a week? Not just a day, but a week? Good enough? Well, thank you all for being here, for sticking it out. I'm going to hang out for a few minutes while I shut everything down if anyone wants to chat with me. Otherwise, I hope you have good weekends. I'll be in Germany for the next 2 weeks, so you won't see or hear from me likely, but I'll be on email eventually if you need anything. So thank you.
Thank you.
And bye for now. Thank you.